Okay, now let's look at the problems from Investigation 23. Okay, number 14. Let G be a group with identity E and let AB be elements of G. Prove that if AB equals BA, then AB to the order of A times the order of B is equal to E. So over here on the right, I put a bunch of facts that might be useful to you. So some of these were facts that I probably should have put on some of the earlier problems that I was going over, particularly these ones. We could have used those earlier. I was just sort of citing them out of my own head. But if AB equals BA, so if A and B commute, then you can do this type of thing. And then every element commutes with itself, so you always have these three properties here. And then I also put the definition for what the order of an element is. So the notation is right down there, but you need all of this stuff right here to understand what the order of an element is. So basically that A and B, that it looks like they're absolute values, those are not absolute values. That's the order of A and the order of B. And the order is the number of elements that are in the cyclic subgroup generated by that element. So in other words, if you take all of the powers of A and you put them in a set and you just count how many there are, that is the order of A. Okay, so it's the number of different powers of A that exist. That's for multiplicative notation, of course. And then theorem 23.5 down here, this is the most helpful one for solving this particular problem. So okay, let's get into this then. So proof. So I'm just going to copy the let statements. So let G be a group with identity E, and let AB be elements of G. Okay, and then I'm going to go ahead and I'm going to assume the if part of the statement I'm trying to prove. So assume AB equals BA. Okay, so now I'm going to try to show this part right here. So show. Alright, so since I assumed that AB equals BA, that does allow me to use theorem 21.4 here. So if AB equals BA, then AB to any power, I can break down and distribute that power. So that's going to allow me to say the following. Then AB to order of A times order of B. I'm going to distribute that power like this. Okay, so that makes it a little bit easier for me. And then what I'm going to do is I'm going to use the third part of theorem 21.5 like this. So I'm going to write A to its own power times B, and then I'm going to do B to its own power. So keep in mind the order of A and B, those are integers, so I can put B inside like that, and then the order of A on the outside like that. So in other words, if you're looking at this theorem 21.5, M and N right there, those are integers, so they do commute with each other. So I can also say that this equals A to the N to the M, like that. So that's basically what I'm doing with B there. Okay, and now finally I'm going to use theorem 23.5. I should probably make some little notes here, some little citations. So like, for example, by theorem 21.4, and then this one was by theorem 21.5. Okay, and then finally by theorem 23.5, I'm going to use the fact that any element raised to its own order is the identity. So let A be an element of G with order n, then A to the n equals E. Okay, so any element to its own order is the identity. So really what I've got here is just the following, like that. So that is by theorem 23.5, and I'm done. So you just had to like look up a bunch of theorems for this one. It's not actually that interesting. Okay, let's look at the next problem. Okay, so let's look at the next problem here. Number 15, the set Z2 cross Z3 is a group under the operation of element-wise addition. Element-wise addition, so what I mean by that is just simply if you add two ordered pairs, each of which has the elements being congruence classes, then you just add the first two together like this. So the first element plus the first element gives you this. And then you add the second two elements as well the same way to get these two here. Okay, so that's all it is. And then, so element-wise addition is defined like that. And then your task is to show that Z2 cross Z3 is actually a cyclic group. So in other words, in order to do that, you need to find a single element of, I should say, of or in Z2 cross Z3 that generates all the elements of Z2 cross Z3 under element-wise addition. Okay, so that's this, we're looking at this definition of a cyclic group right there using additive notation. Okay, so let's go ahead and try this. So proof. Okay, do I have any let statements here? I don't think I do. But let me go ahead and just list out what the elements of Z2 cross Z3 actually are, just so that you know what we're trying to generate. Okay, so it's going to be the following. So we can have 0 and 0, or we can have 0 and 1, or we can have excuse me, or we can have 0 and 2, and then we can have 1 and 0, we can have 1 and 1, or we can have 1 and 2. Okay, so those are all the elements of Z2 cross Z3. Okay, so the element that is actually going to generate all of these under addition is 1, 1. So let me just show you that. So my assertion here is that 1, 1 will generate Z2 cross Z3 because, so let's just go through it. So I'm just going to go through every multiple of 1, 1. So to get the multiples of 1, 1, I'm just going to keep adding 1, 1 to itself. Okay, so first of all, I get just 1, 1 itself. That's obviously one of them. So that's 1 times 1, 1. So that gives me 1, 1. And then 2 times 1, 1. So in other words, this is going to be, so 2 times 1 and 2 times 1. Okay, so here's where it starts to get weird because these are actually not the same thing. So the first one of these congruence classes here, this is congruence modulo 2, and the second one is congruence modulo 3. So 2 times 1 in modulo 2 is 0. So that's going to be 0, mod 2. And then 2 times 1 in mod 3 is 2, mod 3. Okay, so those are two different congruence classes there. It's very strange that you're doing two different versions of 2 times 1 and getting two different answers, but that's because this first element in the ordered pair is in Z2 and the second one is in Z3. Okay, so let's keep going. So 3 times 1, 1 is going to be this. So 3 times 1 in mod 2 and then 3 times 1 in mod 3. So you're getting 3 mod 2 and 3 mod 3, which are two different things. Again, the first one is going to be 1 mod 2, and then the second one is going to be 0 mod 3. Okay, and then we can just keep going. So I'm going to do 4 times 1, 1. So this is going to be, so I'm just going to kind of like try to make this shorter. So I'm just going to write it like this: 4, because this is taking a while, and then 4. Oops, that's not a 4, that's a 3. Okay, so 4 in modulus 2 is the same as 0, and then 4 in modulus 3 is the same as 1. So that's like that. Okay, and then we're kind of running out of room here. Let me try to like make some more room over here. Okay, and then 5 times 1, 1. So this is going to be 5 in modulus 2, and then 5 in modulus 3. So 5 in mod 2 is 1, and then 5 in mod 3 is 2. Okay, and then we just need one more, so 6 times 1, 1 is going to be 6 in mod 2 and 6 in mod 3. So this is going to be, actually they're both 0, because that's 6 is a multiple of 2 and a multiple of 3. Okay, so at this point, I hope what you can see is we've actually gotten all 6 elements that are in that Cartesian product of Z2 cross Z3. So we got 1, 1, we got 0, 2, 1, 0, 0, 1, 1, 2, and 0, 0, and that was all of them. So we've shown that the cyclic group generated by this generator is all of Z2 cross Z3. And that's it. Okay, so number 16, I have actually removed number 16 from the practice test, so that is no longer on there. So let's go ahead to the next problem. Okay, so let's try this next problem here. So let G be a group and let A be an element of G of order n. So for my proof, I'm just going to start by copying those statements down. So let G be a group, I'll just abbreviate like that, and let A in G such that A has order n. Okay, so I want to prove that the order of A to the k is the same as the order of n to the, A to the n minus k. So actually, I think what I can do is a little bit stronger than this even. I can show that those cyclic groups are actually the same. So in other words, I can show the following. We will show that this cyclic group is the same as this one. Okay, so let me show you what I can do here. So first of all, I can write A to the n minus k. I can always write that using this stuff up here as, sorry, that looks like a greater than sign. So I can write this as A to the n times A to the negative k. And then because the order of A is n, that means that A to the n, using this statement here, so from theorem 23.5, then A to the n, A to the negative k is equal to E times A to the negative k, which is just A to the negative k. Okay, so now that I've simplified A to the n minus k into just A to the negative k, I think it should be a little clearer why this is the case. If you look at what the definition of these cyclic groups are, it's just that element raised to every integer. So A to the k, if I raise that to every integer, is actually the same as raising A to the negative k to every integer. So let me just show you why that's the case. So then A to the k is going to be the following. So this is going to be A to the k to the n for all integers in Z. Okay, so this is going to be, I can just rewrite this in the following manner. Let me try to do it in a way that's going to make sense. Okay, so I can multiply k times n like that from this statement here. And I think that's obvious enough, I don't really need to cite it. So if I want to write that out in a longer list, I could do it like this. Let's see, so let me start in the middle. A to the k, a to the 2k, a to the 3k, and so on and so forth. And then going the other way, this would be a to the 0, a to the minus k, and then a to the minus 2k, and then keep going like that in the backwards direction. Okay, and now I hope you see this is actually going to give us exactly the same thing when we do negative k. So this is going to be a to the negative k to the n. And then we're going to get a to the negative kn. And then if we write that out in a long list, we get exactly the same thing. So it's just every multiple of negative k, but since those multiples themselves can be either negative or positive, the multiples of negative k are the same as the multiples of k, all right? So you're going to get exactly the same thing. You're just going to get a to the negative 2k, a to the negative k, a to the 0, a to the k, a to the 2k, a to the 3k, and so on and so forth. Okay, so this shows us that the cyclic group generated by a to the k is actually the same one as the cyclic group generated by a to the n minus k. And so since that's the case, their orders are going to be the same because the order is the number of elements in the cyclic group. Okay, so that's it. Okay, so let's go ahead and do investigation 24. All right, so number 18, I'm going to split this over a couple of slides because it's kind of long, or there's just a lot of parts actually. So let n be an integer with n greater than or equal to 3. If n is even, show that there is at least one element in Dn, so that is the dihedral group. In other words, the group of symmetries on polygons. Aside from the identity that commutes with every element in Dn. And then the hint here is to use these two operations tables, which I've actually put right here. And you're going to look for an element that commutes with everything. So what you're looking for when you're looking for an element that commutes is you want to identify a row and a column that have the exact same entries. So let me just give you an example. So for example, like obviously the identity commutes with everything, so don't look at that one. But for another example, if I look at the row for R1 bar and the column for R1 bar, are these the same? Like, are these entries the same here? Are these entries the same here? Are these two the same here? Are these two the same here? And I think you can see they're not the same. So this would tell us that R1 bar does not commute with everything. Okay, so now what you want to do is you want to look for an element, in other words, a row and a column that are identical, so an element that does commute with everything. So let me just erase this stuff, and then let's look for one that does work. And so this operation table here, this is for the square, and then we'll do it for the hexagon. Okay, so let me see, which one of these actually does commute? So I think I see that R2 does commute. I think we had actually talked about this before in class, that one does work. So R2 looks pretty good. And remember R2, this is the 180 degree rotation. So that's the smallest one, capital R1, that's the smallest rotation. And then if you do that smallest rotation twice for a square, that's halfway around. So that's 180 degrees, counterclockwise, like that. All right, now let's look at the hexagon. So the hexagon, so I think it would make sense to also look for the 180 degree rotation one here. And in that case, the smallest rotation is 1/6 of the way around the circle. So R3 is going to be the one that's actually 3/6 of the way around, or 180 degrees, halfway around. So let's look and see if these are actually identical. So there's two entries missing, but we can use the Sudoku technique to fill those in. So this should be, let's see, the only one that's missing in this row here is R2 bar. And then the only one that's missing in that column now is, looks like R1 bar. Okay, so with those filled in, I hope you can see those are the same row and column. The entries are the same. So again, we're getting the 180-degree counterclockwise rotation for the element that commutes. And now what we want to do is we want to write that element in terms of little r and big R. So remember that little r, that was reflection over a vertical line. And then big R, that was the smallest counterclockwise rotation. So how can we write the 180-degree counterclockwise rotation in terms of little r and big R? Well, we don't need little r because that's a reflection. We just need the rotations. So how many times would you have to do that smallest rotation in order to get halfway around the circle? So this is where it becomes important that n is even. So because n is even, that means that big R is a counterclockwise rotation 1/n of the way around the circle. Okay, so to go halfway around the circle, 180 degrees, that would mean you would have to go n/2. You would have to do that big R thing n/2 times. So in other words, that 180-degree rotation, that's going to be big R raised to the n/2. So basically you're doing that smallest counterclockwise rotation n/2 times. That's going to take you halfway around the circle. Obviously doing it n times, that would take you all the way around the circle. So anyway, this is the element that we're looking for, that we are going to show commutes with everything. Okay, so on the next slide we will prove that that actually commutes with everything. Oh, and by the way, I forgot to mention, but it's important that n is even, because otherwise n/2 is not an integer. So this, if n is not even, then r to the n/2 would not even be an element of the dihedral group. Okay. All right, so now on this slide, let's see if we can actually prove that the element we found commutes. So we're going to try to prove that r to the n/2 commutes with all of dn when n is even. Okay, so let's go ahead and start the proof. So I'm going to assume that n is an integer, that n is greater than or equal to 3, and that n is even. Okay, and now since n is even, let's just say since n is even, let's actually call n equal to 2k for some integer k. Okay. All right, so then now what we want to show is we will show that r, so it's going to be r to the n/2, which is going to equal r to the k, commutes with all, I'll just call the elements of the dihedral group, I don't know, d. So with all d and dn. Okay, so in other words, that r to the k d equals d r to the k. Okay, so how am I going to do this? All right, so let's just say that d is some element of the dihedral group. Then we know that we can write the elements of the dihedral group in these forms here. So that is all the elements of the dihedral group up there. So in other words, we can write d in the following manner. So d equals, so it either starts with little r or it doesn't. So I'm going to put little r to an exponent. I'll just call it I. Actually, maybe I won't call it I because I already used k, so that may be confusing. I will call it r to the, oh, I don't know. Okay, let's just call it I. I give up. Okay, so r to the I times big R, and okay, let's just call that j. Okay, so little d can be written in this form, and then these exponents I and j, we're trying to say that little d can be any element of the dihedral group. So I and j, obviously, they need to be integers. And then furthermore, I is either going to be, I is actually either 0 or 1, and j is in the range from, so j can be 0 as well, or 1 or 2, all the way up through the largest it can be is n minus 1. Okay, so that is what all of the elements of the dihedral group look like. And now that I've written that element that I selected in that form, I just want to show that r to the k commutes with that. So in other words, we will show, and I'm just putting this in brackets because it's an optional statement, that r to the k times r to the I, r to the j equals r to the I, r to the j, r to the k. Okay. All right, so let's go ahead and try doing this. So the only thing I really have in my arsenal, there's only a couple of things that I can really use here, and that's these. So I know that I can move capital R to some power. I can move that to the other side of little r if I make that power negative. So if I swap it from being I to negative I. And then I also know the following, that capital R to the n equals the identity, and r squared, oops, I think I actually left this out, but that's supposed to say r squared equals I. So I can also use that if I need to. Okay, so let's go ahead. So I'm going to say r to the k, little r to the I, r to the j. Okay, so I know that I can move r to the k to the opposite side of little r to the I if I make the power negative. So I know this, so r to the negative k, and then r to the j. Okay, and now that I have those r's together on the other side, what else could I do? So I think I can do the following. I can always multiply in anywhere that I want. I can multiply the identity. That won't harm anything. So I'm going to say r to the negative k, that's the same, and then r to the j. Okay, and then what I can do is I can replace the identity from up here with r to the n. So this is going to be r to the I, r to the n, and you guys will see why this actually helps. R to the j. Okay, and then remember that n is actually 2 times k, so I'm going to make that 2k, r to the negative k, r to the j. Okay, and then, all right, so now at this point what I can do is I can actually combine all of those powers of capital R. You can always combine powers of a single element. You just can't always sort of distribute and combine from more than one element unless the group is abelian. But since this is just one element, capital R, I can do this plus j. Okay, so now that I have it like that, I can simplify that exponent, and this will be capital R to the k plus j. Okay, and now you see how this is going to work out. So now what I've got is I can split again and get little r to the I, and then this can give me capital R to the j, and then capital R to the k. Okay, and at this point I'm actually done. So I started here with r to the k on the left, and then over here it's on the right. So I have showed that r to the k commutes with any element of the dihedral group. And that's it. Okay, so let's look at number 19 here. So the dihedral group Dn has this presentation here. So using little r and big R and these 3 equations, show that Dn also has this presentation here. So here they're using little a and big A, and it's actually, it looks like it's still 3 equations where it's a squared equals 1 and b squared equals 1, and then ab to the n also equals 1. And then where little a equals little r and little b equals little r big R. So the hint here is just to show that the relations for the first presentation imply the relations for the second presentation when you make that particular substitution for A and B. So let's go ahead and try it. So, proof. I'm just going to go ahead and let A equal R and B equal little r big R. So let's just go through and one by one try to show first of all that a squared equals 1, and then that b squared equals 1, and then that ab to the n equals 1. So let's start with a squared. So then a squared, I said that a is r, so this is r squared. Okay, well, one of the relations for the dihedral group is that r squared equals 1. All right, that was easy. Let's see if b squared is just as easy. Okay, then b squared, so what would b squared be? So we said that b was little r big R, so that's squared. Now be careful, you cannot distribute that 2 to both the little and the big R because this group is not abelian. Okay, so all we can really do is we can just write this as little r big R times little r big R. Okay, but we do know one of the relations for the dihedral group is that little r big R equals big R inverse times little r. So if we want to, we can make that replacement. So I think I'm just going to do that on the second one there. So I'll leave the first one as little r big R, and then I'll replace the second one with big R inverse little r. Okay, and then what happens, those two cancel out. So this gives us little r squared, which is 1. Okay, so we showed that b squared also equals 1. And now let's finish by showing that ab to the n equals 1. So finally, ab to the n. So let's see, ab is going to be, let's see, that's little r, and then little r again times big R, and that's to the n. Oh, okay, so this is not very hard at all. So I have r squared there, so this is r squared big R. So r squared is 1, so this is just 1 times r to the n, so that's just r to the n. This 1 is the identity. And then r to the n is also defined in the relations for the dihedral group as being 1, so that's 1. Okay, and that's it. Okay, so let's look at number 20. So let X be a group with presentation xy, little x, little y, and these three relations right here show that little x equals x to the fourth. And then the hint here is to start with the fact that little x equals little x times y squared, because y squared equals 1, so of course we can start with x equals x and then multiply the right hand side by 1 and replace 1 with y squared. And then repeatedly replace instances of xy on the right hand side with yx squared. Okay, so let's give a try at doing this. It sounds like it might be a little tricky, but let's do it. Okay, so we start with the fact that x equals xy squared, just like we're told. And now we're going to repeatedly replace instances of xy on the right hand side with yx squared. Okay, so it sounds like what I need to do is separate this into xy times y, and then I'm going to replace the xy part with, because up here it says xy equals yx squared, so this is going to be yx squared, and then y again. Okay, and then it says to repeatedly do this, so I guess I need to find another place where xy appears on the right hand side. So let's see, where else does it appear? So this can be written as yx times xy, like that. And then, so I can replace the xy part with, again, yx squared. Okay, still not to x to the fourth yet, so let me keep going. So I can write this as y times xy, so I'm just moving the parentheses because the operation is associative. So I can replace xy again with yx squared. So this is going to be y times yx squared times x squared. Okay, I think I see how this is going to finish now. So this is going to be y squared x to the fourth, and then we know that y squared equals 1, so this is actually just x to the fourth. Okay, so I did it. And that's it. Okay, so let's look at the problems from investigation 25. All right, 21. Prove that for n greater than or equal to 2, Sn is non-abelian. Okay, so over here on the right, I just put the things that you would need to understand the definition of what Sn is. So that's all this stuff here. And then I also put the definition of a cycle because I think I'm going to use a cycle to prove that Sn is non-abelian. Okay, so all I really need to do for this problem is to just show that there are two elements that do not commute. So why don't I just try two random elements and just see if they commute? So I wanted to do it in terms of cycles instead of in terms of the permutation notation where you have the top and the bottom, because cycles can be written the same way for any value of n, whereas that other permutation with the two rows, the top and bottom row, that requires you to know what n is. So I'm going to use cycles. So proof. Let's just try using 1, 2, oops, it's not with a comma, sorry. 1, 2, and I don't know, 2, 3. So 1, 2, and 2, 3 are n, s, n for n greater than or equal to 2. So let's just see if they commute. So 1, 2 times 2, 3. Okay, can I write this as one cycle? So let's see. So remember 2, 3 gets applied first. So 2 gets moved to 3, and then 3 gets moved nowhere, so that 2 will be moved to 3. Okay, and then what happens to 3? So 3 gets moved to 2 by this part, and then 2 gets moved to 1 by this part. So that'll be 1. Okay, and then let's just make sure, let's see, 1 doesn't get moved here, and then 1 does get moved to 2. Okay, so that is 2, 3, 1. And then let's try it in the other order. So 2, 3, and then 1, 2. Okay, so I'll just start with 2 again like I did on the last one. Okay, where does 2 get moved? So first 2 gets moved to 1, and then 1 doesn't get moved anywhere in the other cycle. So 2 just gets moved to 1. And then what happens to 1? So 1 gets moved to 2, and then 2 gets moved to 3. So in all, 1 gets moved to 3. And then what happens to 3? So 3 doesn't get moved in here at all, and then in this one 3 gets moved to 2. So it's just this cycle, 2, 1, 3. Okay, so I think you can see these are not the same cycle. So 2, 3, 1 does not equal 2, 1, 3. So Sn is not abelian. And that's it. Okay, so let's do number 22. Prove that the only element that commutes with every element in Sn is the identity permutation I. Okay, so what I'm going to do is I'm just going to show that every element that is not the identity has some other element that it does not commute with. Okay, so I'm going to start by saying let sigma be an element of the symmetric group such that sigma is not the identity. Okay, so since sigma is not the identity, I know that sigma has to move at least one element, so I can say there is some I such that, actually let me say I and j, such that sigma of I equals j. So in other words, sigma must move some element, and I'm just calling that element I and the output j. Okay, then let me make an element that does not commute with sigma. So I'm going to define, let's call it tau. I'm going to let tau be the cycle I, k, where j does not equal k. So I want tau to be an element that permutes I with something that is not j. Okay, now I'm going to show that sigma and tau do not commute with each other. Okay, so let's try doing sigma of tau of I. So sigma tau of I, in other words, sigma of tau of I will be the following. So first I plug I into tau, and so that tau of I is going to be k, because tau just transposes I and k. So this is going to be then sigma of k. And I don't actually know what sigma of k is, but one thing I know about it is that it's not j, because sigma moves I to j, and k and I are supposed to be different. I probably should have said that. And I also does not equal k. Okay, so this, whatever it is, it's not going to be j that I get out from sigma there. Okay, and so now let me do this in the other order. So tau of sigma of I, which I can write in parentheses like this. So remember that sigma of I is supposed to be j, and tau only transposes I and k, and so it doesn't move j at all. J is not one of those two elements there. So maybe I should have said that as well. So let me add a little note here. J is also not equal to I. So these are three distinct elements, I, j, and k. Okay, so when I plug j into tau, j does not move, or tau does not move j, so I just get j back out. And so what you can see here is that sigma of tau of I is not the same as sigma of tau of, oh, sorry, the other way around. It's not the same as tau of sigma of I. So sigma does not commute with everything in the symmetric group because it doesn't commute with tau. Right. So yeah, that shows that any element sigma that is not the identity will not commute with everything in the symmetric group. And of course it should be obvious that the identity commutes with everything. So that's all we need. Okay, number 23. When is the cycle A1, A2, A3, ... AK in Sn even, and when is it odd? And prove your answer. So this is actually really easy, probably too easy, because there's a very specific way to write any cycle, A1 through AK, and you can just write it like this. And then we have this theorem that says that no matter how you write a cycle as a product of transpositions, that the parity of the transpositions, the evenness or oddness, will always be the same. So all we really need to do is just say that A1, A2, A3, ... up through AK is equal to A1, A2, and then A2, A3, A3, A4, ... AK minus 2, AK minus 1, and then AK minus 1, AK. And so how many transpositions was that? So this is a product of, okay, so how many were there? Let's see, if we use the first number in each transposition and we count by the subscripts there, it goes 1, 2, 3, and then it stops at k minus 1. So this is a product of k minus 1 transpositions. Okay, so the cycle A1, A2, A3, ... AK has the same parity as k minus 1. In other words, so let's see, so if k is odd, okay, so if k is odd, then k minus 1 will be even, so the cycle will be even. So A1, A2, A3, ... k is even, and if k is even, then k minus 1 will be odd, so this will be odd. And yeah, that's it. So it's not very complicated. Okay, so number 24. Let G be an abelian group and let H equal x squared such that x is an element of G. Prove that H is a subgroup of G. Actually, I'm not sure why this problem was in section 25 or investigation 25, but anyway, I found it in the homework there. So let's give this a try. So we're going to prove that H is a subgroup of G. Okay, so proof. So I'm just going to copy the let statements. Let G be an abelian group, and let H equal this set x squared such that x is in G. Okay, so we want to prove that H is a subgroup, so we just have to do the 3 conditions of the subgroup test. Okay, so part 1, we need to show that H is closed. So closed. Alright, so I'm gonna let, let's call it, I don't know, H and K. Let H and K be elements of capital H. So that means there are some elements, I don't know, X and Y, let's say, in the group, such that H equals X squared and K equals Y squared. So now I want to show that HK is also an element of capital H. Okay, so then little h, little k is equal to x squared, y squared. And now it's important that the group is abelian, because at this point what we need to do is say that this is xy squared. So because G is abelian. And then we can say, since G is closed, that means little xy is in G. So little xy squared would be in H, because xy is an element of G. Okay, so this means that HK, little hk, is in capital H. So capital H is closed. Okay, so we got the first condition. Let's go ahead and try the second one. Okay, number 2. We need to show that H contains the identity element. So this is not very hard, I think. Usually this is the easiest one. So identity, so E squared is equal to E. Actually, maybe I should say it this way. E squared is in H because E is in G, and E squared equals E. So E is in H. All right, and now part 3. So we need to show inverses. H contains inverses. Okay, so let little h be in big H. Now I want to show that little h inverse is also in big H. So what do I get from letting little h be in big H? This means there is, I'll call it x in G, such that little h equals x squared. Okay, then h inverse would be x squared inverse. So that would be, remember, you can use rules of exponents on a single element, you just cannot use them on more than one element at a time unless the group is abelian, although in this case it is abelian, so I guess it doesn't really matter. But anyway, this is going to be x to the negative 2, and that is the same as x to the negative 1 squared. Okay, and then since G is a group, x to the negative 1 is in G, so that would mean x to the negative 1, so x to the negative 1 squared would be in capital H. So that means H inverse is in capital H. Okay, so H does contain inverses. All right, so that's it. We did the 3 parts. So that means capital H is a subgroup. Okay, so that's it, everybody. So the PDF of these solutions will be up on the usual place on Blackboard with the other practice test solutions. The solutions are going to be a little sloppier than usual because I was writing on the screen. Sorry about that, but you can watch this video while you are working on your real test or anytime you would like. And I hope this was helpful to you. Email me if you have any questions about these solutions or how I did the problems, or if you just want to do like a video chat and ask for some help, just send me an email and let me know, and I'll be happy to help. All right, see you next time.